February 1932, East Hartford, Connecticut. Hamilton Standard Propeller Corporation. In a gray, oil-stained test facility, Frank Walker Caldwell stood before a gleaming metal propeller spinning at 2,400 revolutions per minute. 3 aluminum blades, unlike anything the aviation world had seen. Variable pitch, hydraulically controlled, a system the Army Air Corps had dismissed as impossible. Caldwell adjusted the oil flow and watched the blades shift their angles seamlessly. Fine pitch for the simulated climb, coarse pitch for cruise, feathering when engine failure was simulated. Numbers flashed on his clipboard. RPM steady at 2,400, thrust increasing incrementally as the blades responded automatically to changing load. The math worked. The theory was sound, but the world outside the lab remained skeptical. Experts called the concept too complex, too fragile, too ambitious. 3 days earlier, a call had arrived from Boeing Field in Seattle. A Model 247 airliner had stalled over Denver, unable to climb over the Rockies. The wooden propellers, fixed in a single pitch, had left the aircraft helpless. Caldwell's impossible design was the only hope. If it worked here, it could save aircraft, airlines, and lives. Caldwell initiated the test flight simulation. Data streams recorded climb rates, RPM stability, thrust efficiency, and fuel consumption. Takeoff equivalent reduced by 30%. Climb rate increased by 40%. Service ceiling improved by 7,000 feet. The constant speed propeller wasn't just theory, it was engineering realized. Yet Caldwell knew that numbers alone wouldn't convince anyone. The breakthrough would require real-world proof, unassailable, evidence that the invention could survive the rigors of flight. One flawless demonstration, one perfect climb over the Rockies, and the impossible would become undeniable. But failure was not an option. A single misstep, a single miscalculation could destroy his career and the future of American aviation innovation. As the test cycle ended, the blades slowed, still gleaming under the flickering workshop lights. Caldwell's eyes narrowed. Every calculation, every sleepless night, had led to this moment. The future of flight rested on 3 spinning aluminum blades, and on the resolve of the man who refused to let conventional wisdom dictate what was possible. Frank Walker Caldwell was born in 1889 in the industrial heart of New England. From a young age, he displayed an instinctive understanding of machines. Gears, levers, and rotating shafts fascinated him more than toys or games. By the time he entered MIT, his mind was already tuned to the rhythm of engineering precision. He graduated with a mechanical engineering degree, his notebooks filled with calculations and sketches of devices that seemed impossibly ambitious to his peers. In 1917, the United States entered World War I. Caldwell joined the government as the chief propeller engineer charged with advancing military aviation at a time when aircraft were fragile, slow, and unreliable. His early work revealed an industry resistant to change. Wooden propellers were the standard. Metal seemed too heavy, too brittle, too dangerous. Adjustable propellers were dismissed as unnecessary complexity. Yet Caldwell's experiments demonstrated the superiority of metal, ground-adjustable designs. Time and again, his numbers proved the doubters wrong. By 1932, Caldwell had joined Hamilton Standard Propeller Corporation in East Hartford, Connecticut, bringing with him decades of experience. He had seen the evolution from fragile wood to reliable metal. He understood every variable: blade shape, pitch, RPM, thrust, and airflow. But what set him apart was his conviction that mathematics, not opinion, dictated truth. While colleagues debated theoretical advantages, Caldwell focused on the numbers, trusting data over discussion. The inspiration for the constant speed propeller came from observing the limitations of fixed pitch and two-position adjustable propellers. Aircraft were hampered at high altitudes, inefficient at cruising speeds, and vulnerable in climb performance. A pilot's life depended not on courage alone, but on how effectively an aircraft could convert engine power into thrust. For Caldwell, the solution was clear: a propeller that automatically adjusted blade angle to maintain optimal RPM across all flight conditions. Yet the idea was met with near-universal skepticism. The Army Air Corps had deemed hydraulic adjustment impractical. Charles Lindbergh privately questioned the system's reliability. Industry experts warned that moving parts would fail at altitude, that oil viscosity would sabotage the mechanism, that vibration and cold would turn innovation into disaster. To them, Caldwell's vision was a theoretical curiosity, not a practical solution. Caldwell's personality suited the challenge. Methodical, meticulous, and unflinching, he could spend hours analyzing test data, recalculating pressures, or refining tolerances to the thousandth of an inch. He demanded the same precision from his team, fostering an environment where experimentation was relentless but controlled. Every test cycle was documented, every anomaly dissected, every failure a lesson rather than a setback. The East Hartford test facility became his laboratory, his proving ground. Oil stains marked the floors, gauges flickered with numerical precision, and spinning propellers became the pulse of his work. It was here, in this seemingly mundane industrial environment, that Caldwell transformed aviation theory into tangible results. Here, he developed the three-bladed hydraulic system that would later be hailed as revolutionary. Fine pitch for takeoff, coarse pitch for cruise, and automatic feathering in case of engine failure. Caldwell's early years at Hamilton Standard were a delicate balance of innovation and persuasion. Orders and funding depended on convincing skeptical executives, pilots, and engineers that his design would work. He relied on data, demonstrations, and prototypes, letting numbers do the talking. Yet, he understood that the final proof required flight testing. Aircraft in the air, blades spinning, engines under stress, and RPM holding perfectly at every altitude. Even within Hamilton Standard, opposition existed. Some engineers warned that the complexity would invite disaster. Others questioned whether American factories could produce blades and governors with the precision his designs demanded. Caldwell responded systematically, designing test rigs, endurance cycles, and stress simulations. He treated every variable, hydraulic pressure, oil temperature, RPM fluctuation, as a critical parameter. Success, he knew, depended on eliminating every uncertainty before the propeller ever left the factory. By the end of 1932, Caldwell had laid the foundation for what would become the impossible propeller. His team had tested prototypes, verified calculations, and documented results that consistently outperformed fixed-pitch and two-position designs. Yet the aviation world remained unconvinced. Skepticism was as much a part of the environment as the spinning blades themselves. But Caldwell's philosophy was simple. Innovation was measured not by consensus, but by results. And results, he was certain, were only a flight test away. The WWII stage was set for a breakthrough that would redefine aircraft performance and cement his place in aviation history. The winter of 1932 was bitterly cold in East Hartford, but inside Hamilton Standard's test facility, the air vibrated with the energy of innovation. Frank Caldwell's prototype constant speed propellers spun endlessly on test stands, subjected to simulated loads that far exceeded what any aircraft would encounter. Each rotation was a calculation, each adjustment a proof of concept. The problem, as Caldwell saw it, was not theory. It was convincing the world that his design could survive the unforgiving realities of flight. The first prototype failed spectacularly. Hydraulic governors leaked, oil lines burst under pressure, and a propeller blade cracked under simulated aerodynamic stress. To any outsider, the project seemed doomed. But Caldwell's response was methodical. He recorded every failure, traced each to its root cause, and redesigned. A burst line became a thicker steel conduit. A cracked blade became a subtly reinforced aluminum alloy. The hydraulic governor was recalibrated to operate within precise tolerances. Every iteration brought the prototype closer to perfection. Meanwhile, requests for demonstration flights began arriving from the aviation industry. Boeing, struggling with the Model 247 airliner, had a clear problem. Their fixed-pitch wooden propellers could not generate sufficient thrust to clear Denver's high-altitude airspace. Caldwell's constant speed design promised a solution, but Boeing executives were wary. The stakes were high. Failure in flight would not only destroy the aircraft, but also risk Caldwell's reputation and Hamilton Standard's credibility. Caldwell oversaw the retrofit of a Model 247 with a prototype constant speed propeller. Test pilot Eddie Allen, a former Navy aviator renowned for his cool demeanor, prepared for the first real trial. Caldwell had already simulated the flight thousands of times in the lab, but the true measure of success lay in the mountains. Takeoff was textbook. The fine pitch blades allowed the engines to generate maximum thrust, lifting the aircraft off the runway in record time. Numbers on Caldwell's clipboard verified the improvement. A 30% reduction in takeoff distance, 40% increase in initial climb rate. The plane ascended steadily, the hydraulic system automatically adjusting blade angle to maintain optimal RPM as air density dropped. At 6,000 feet, 10,000 feet, 15,000 feet, the aircraft climbed effortlessly. By 20,700 feet, far higher than any Model 247 had previously reached, the plane achieved its service ceiling. The results were undeniable. Speed across all altitudes increased by 15 milliradians, fuel efficiency improved by 12%, and engine stress remained well within safe limits. The impossible, long dismissed by industry experts, had been realized. Caldwell's TWWII design had not only solved a practical problem but exceeded all expectations. Even so, victory was only the beginning. Caldwell knew that scaling this innovation to military aircraft would be far more complex. Each fighter and bomber posed unique challenges, different engine outputs, airframe configurations, and operational requirements. For the next 2 years, Caldwell and his team refined blade shapes, hydraulic governors, and feathering mechanisms, subjecting each new prototype to rigorous tests. One early challenge involved the reliability of the feathering system. In theory, if an engine failed, the propeller blades could align parallel to the airflow, reducing drag and allowing the aircraft to maintain control. In initial tests, slight hydraulic inconsistencies caused partial feathering, creating enough drag to threaten the airframe's stability. Caldwell solved the problem with redundant hydraulic circuits and a mechanical backup system, ensuring that even under partial failure, the propeller would perform its critical function. Another obstacle was temperature extremes. At high altitude, oil viscosity increased and metal contracted, threatening both blade pitch accuracy and hydraulic responsiveness. Caldwell devised a series of environmental tests that simulated altitudes of 35,000 feet, temperatures from 40 degrees below zero to 160 degrees Fahrenheit, and continuous operation under maximum RPM. Each failure informed a redesign. Seals were improved, oil formulations modified, and governor tolerances recalculated. The result was a propeller system that performed better at high altitudes than at sea level, the exact opposite of what skeptics had predicted. Incrementally, Caldwell's designs proved themselves. Simulated combat maneuvers, high-speed dives, extended climbs. The constant speed propellers excelled. Every measurement aligned with his calculations. Climb rates increased 40%. Service ceilings extended 7,000 feet. Cruise efficiency improved 15%. Yet the true test was not in numbers alone. It was in reliability, consistency, and the ability to withstand stress far beyond normal operational conditions. By the end of 1934, Caldwell had transformed what was once considered impossible into a robust, field-ready technology. The industry's skepticism was gradually replaced with cautious respect. Aircraft manufacturers, airlines, and military advisors began requesting demonstrations, all eager to see whether the numbers could survive real-world conditions. But Caldwell remained unsatisfied. He knew that operational adoption would demand more than lab success. It required mass production, stringent quality control, and proof that his propellers could perform flawlessly under the stresses of constant flight. Each prototype, each test flight, each incremental improvement was a step toward that ultimate goal. The breakthrough was no longer theoretical. Caldwell had built a system that solved a fundamental problem of aviation, maintaining optimal engine performance across all flight regimes. Yet he also knew that engineering success alone would not guarantee acceptance. Convincing the industry, scaling production, and proving reliability at mass scale would test his skills, patience, and ingenuity like never before. In those early years, Caldwell demonstrated not only the brilliance of his design, but also the methodical determination that defined his career. The impossible propeller had survived its first flights, weathered initial failures, and emerged as a reliable, revolutionary technology. The stage was set for wider adoption, and the coming years would prove whether his creation could truly transform American aviation. By 1935, Caldwell's constant speed propeller had proven its mechanical reliability, but the broader significance of his invention was only beginning to be understood. The aviation industry had long been constrained by the limits of fixed-pitch or two-position propellers. Takeoff distances were longer, climb rates lower, service ceilings inadequate, and fuel efficiency inconsistent. Pilots had to manually adjust pitch mid-flight, often during critical maneuvers. Caldwell's design promised not just incremental improvement, but a complete transformation of aircraft performance. The strategic importance was clear. Aircraft equipped with constant speed propellers could climb faster, reach higher altitudes, fly longer distances, and operate more efficiently. For commercial aviation, this meant planes could traverse mountain ranges, maintain tighter schedules, and carry heavier loads without sacrificing performance. For the military, it meant fighters and bombers could reach intercept altitudes sooner, escape threats more effectively, and exploit engine performance across every flight regime. In essence, the propeller became a force multiplier, extending the capabilities of existing airframes without modifying engines or airframes themselves. Caldwell's calculations quantified these advantages with precision. A fighter retrofitted with his three-blade, hydraulically controlled propeller could reduce takeoff distance by up to 30%, increasing operational flexibility in smaller or hastily constructed airfields. Climb rates improved by 40%, allowing aircraft to reach engagement altitudes minutes faster than opponents. Service ceilings increased by 7,000 feet, giving a tactical altitude advantage that could determine the outcome of any engagement. Fuel efficiency improved 15%, extending range and endurance, critical factors for both commercial and military operations. Even skeptics had to acknowledge the elegance of Caldwell's design. While critics had argued that complexity and moving parts would compromise reliability, Empirical evidence demonstrated the opposite. Automatic pitch adjustment reduced mechanical stress on engines, prevented overspeed damage during dives, and mitigated vibration that could fracture hubs and loosen mounting bolts. Redundant hydraulic circuits and mechanical backups ensured that even in the event of a system failure, the propeller would maintain basic function, often preventing catastrophic outcomes. Caldwell's work also had a ripple effect across the American aviation industry. Hamilton Standard's success prompted manufacturers to re-evaluate assumptions about engineering complexity. Components previously dismissed as too fragile or too sophisticated became viable, provided they were designed, tested, and manufactured with the precision Caldwell demanded. Engineers began to think in terms of systems rather than isolated parts, recognizing that coordinated mechanisms could outperform simpler designs in both performance and reliability. The industry's growing recognition of Caldwell's propeller coincided with rising global tensions. European and Pacific powers were expanding their air forces, accelerating research into faster, higher-flying, and more agile aircraft. The United States, though officially neutral, recognized that superior engineering could provide a decisive advantage should conflict arise. Caldwell's propeller was not merely a technical achievement, it was a potential strategic asset, capable of tipping the balance in favor of any force that could adopt it rapidly and effectively. Within Hamilton Standard, Caldwell oversaw the transition from prototype to production readiness. He implemented meticulous quality control, knowing that even minor deviations in blade geometry or governor calibration could compromise performance. Every hydraulic piston, gear assembly, and blade attachment was measured, tested, and documented. Statistical analysis of test data revealed patterns of potential failure, which Caldwell addressed proactively, refining tolerances and redesigning components before they became systemic issues. The stakes were immense. A single faulty propeller in a military aircraft could result in mission failure, loss of strategic advantage, or even casualties. Caldwell's rigorous approach ensured that every unit leaving the factory performed within predictable, reliable parameters. His insistence on precision and redundancy elevated the standard for the entire industry, creating a model for military-grade engineering in a civilian-dominated sector. Caldwell also recognized the importance of communication. He prepared detailed, technical reports, presenting data in terms that pilots, engineers, and executives could understand. Charts demonstrated climb curves, RPM stability, thrust measurements, and fuel efficiency gains. Comparisons to fixed-pitch and two-position propellers made the advantages tangible. Caldwell did not rely on persuasion alone. He relied on incontrovertible numbers that demanded recognition. By 1936, the constant speed propeller had become more than a laboratory curiosity. Airlines requested retrofits to enhance operational reliability in challenging terrain. Aircraft manufacturers began integrating Caldwell's designs into new models, recognizing the potential to market planes with superior performance. Military planners took note, even if bureaucratic processes slowed adoption. The combination of validated data, operational reliability, and strategic significance made the propeller an essential piece of American aviation infrastructure. Caldwell's scientific foresight in emphasizing both performance and reliability would pay dividends in the years ahead. As aircraft speeds increased and altitudes rose, the limitations of fixed-pitch designs became more pronounced. Pilots, engineers, and decision-makers who had once doubted Caldwell's impossible invention now faced the reality that mastery over propeller pitch could define the difference between operational success and catastrophic failure. In the broader context of aviation history, Caldwell's propeller represented a fundamental shift. Engineering precision and adaptive mechanisms could overcome constraints that had limited aircraft performance for decades. It was an innovation that leveraged mathematical certainty, mechanical elegance, and relentless testing to achieve results that seemed impossible to those constrained by conventional wisdom. The stage was now set for the propeller's real-world adoption and its dramatic impact on American aviation capability. Caldwell had proven the technology's merit. The challenge ahead was scaling production, ensuring battlefield-grade reliability, and demonstrating that his impossible design could transform the operational potential of every aircraft. It touched. By 1937, Caldwell's constant speed propeller had proven its superiority in controlled tests, but the transition from laboratory success to operational adoption posed its own challenges. Hamilton Standard faced an immediate and daunting crisis. Production capabilities were limited, demand was growing, and military skeptics remained unconvinced. Caldwell understood that bridging the gap between prototype and widespread deployment would test his engineering acumen, logistical skills, and personal resolve. The first major adoption challenge emerged when the Army Air Corps requested demonstration flights for operational assessment. Caldwell retrofitted a series of P-26 P-shooter fighters with his propeller system, ensuring each installation adhered to exacting specifications. The hydraulic governors were calibrated to maintain precise RPMs during climbs, dives, and turns. Redundant circuits were tested repeatedly, with every failure scenario simulated in painstaking detail. Minor errors were unacceptable. The system had to perform flawlessly under all foreseeable conditions. Early demonstrations produced remarkable results. Takeoff distances were reduced by 30%, climb rates increased by 40%, and service ceilings were elevated by 7,000 feet. Maximum speeds improved by 15 to 20 pointers, while fuel efficiency rose by 12%. These gains were more than incremental. They fundamentally altered the aircraft's operational envelope. Caldwell's propellers enabled planes to reach higher altitudes faster, accelerate more effectively, and conserve fuel, advantages that could define mission success or failure. Yet the successes did not erase skepticism. Army engineers questioned the reliability of hydraulic systems under combat stress. What would happen if oil pressure dropped at high altitude? Could the propeller fail in mid-flight, endangering pilots? Caldwell's answer was methodical. Data, testing, and demonstration. He designed the whirl test, a system that mounted propellers on fixed stands to measure thrust, endurance, and structural integrity under extreme conditions. He subjected every component to vibration, temperature extremes, and hydraulic stress, far exceeding operational limits. Caldwell's meticulous testing silenced much of the skepticism. Army officers witnessed prototypes endure simulated combat, maneuvers without failure. Hydraulic governors maintained RPM within tight tolerances. Blades shifted smoothly between fine and coarse pitch. And the feathering system functioned flawlessly even when one engine was rendered inoperative. It was not only engineering excellence, but reliability proven beyond dispute. The next hurdle was industrial adoption. Hamilton Standard's East Hartford factory was modest, originally producing components for Lindbergh's Spirit of St. Louis. Scaling to meet military demands required new assembly lines, trained workers, and rigorous quality control procedures. Caldwell personally oversaw the expansion, insisting on 3-shift operations and meticulous inspection of every blade and governor assembly. Each propeller was measured to thousandths of an inch, each hydraulic circuit pressure tested, and every component documented before shipment. Even with these measures, early production batches revealed the fragile nature of complex manufacturing. Minor deviations in assembly could cause feathering mechanisms to malfunction or governors to misbehave at high altitudes. Caldwell responded with immediate redesigns, introducing redundant pressure circuits, backup mechanical linkages, and enhanced environmental testing protocols. No propeller left the factory without his personal approval. By late 1938, Caldwell's propeller was poised for full-scale adoption. Army Air Corps orders increased, followed by Navy interest, and commercial airlines began requesting retrofits to improve climb performance and fuel efficiency. Caldwell worked tirelessly, traveling between East Hartford, test fields, and assembly lines, ensuring that every design nuance was maintained at scale. Each success reinforced the system's reliability and strategic value, while every minor setback became an opportunity for innovation. A pivotal moment arrived during a demonstration with identical P-26 fighters, one with a fixed-pitch propeller, the other with Caldwell's constant speed system. Observers noted the difference immediately. The fixed-pitch plane required 320 yards to lift off. Caldwell's prototype, 225 yards. Climb to 20,000 feet took 8 minutes, 30 seconds for the old system. 5 minutes 40 seconds for Caldwell's. Maximum speed increased from 187 mph to 203 mph. Service ceiling rose by 6,500 feet. Observers, initially skeptical, were forced to acknowledge that the impossible propeller had transformed the aircraft's capabilities. Despite these demonstrations, Caldwell faced bureaucratic resistance. Military procurement officers feared logistical complexity, maintenance challenges, and pilot adaptation. Caldwell countered with rigorous data, detailed training manuals, and continued improvements in hydraulic reliability. He personally supervised installations, calibrations, and test flights, demonstrating that operational adoption was not only feasible, but advantageous. By 1939, the adoption process accelerated. Hamilton Standard expanded the East Hartford factory to operate 3 shifts, 7 days a week. De Havilland and Boeing engineers worked under Caldwell's guidance to integrate the propellers into new aircraft models. Training programs ensured pilots understood automatic pitch adjustment, while maintenance crews were instructed in redundant systems and emergency procedures. Caldwell treated the transition as both an engineering and operational challenge, aware that widespread adoption depended on flawless integration at every level. During this period, Caldwell also innovated production techniques. Precision machining, of 47 components per propeller, required tolerances measured in thousandths of an inch. Assembly procedures demanded skilled labor using specialized tools. Caldwell implemented statistical process control, monitored batch consistency, and instituted environmental testing for every unit. Even small errors in manufacturing were unacceptable. A single faulty propeller could undermine confidence and jeopardize mass adoption. Operational testing continued in parallel. Caldwell supervised climbs, simulated engine failures, dives, and prolonged endurance flights. Each test reinforced the reliability and performance claims. Takeoff distances shortened, climb rates increased, service ceilings improved, and maximum speeds rose. The feathering system, once a source of concern, now consistently eliminated drag during engine failure simulations, enabling aircraft to maintain control and continue missions without intervention. Caldwell's relentless oversight ensured that the propeller's adoption was not merely theoretical, but practical, scalable, and reliable under real-world conditions. By 1940, the system had been installed on multiple aircraft types across the Army, Navy, and commercial aviation sectors. The combination of performance improvement, mechanical reliability, and operational feasibility made Caldwell's constant speed propeller an undisputed engineering achievement. The impossible propeller had moved from prototype to mass adoption, overcoming skepticism, logistical challenges, and manufacturing limitations. Caldwell's work had transformed aircraft performance, demonstrating that meticulous engineering, rigorous testing, and unwavering commitment to quality could overcome even the most entrenched doubts. The crisis of adoption had been met and conquered, setting the stage for the propeller's decisive impact on American aviation capability in the years to come. By 1941, the world was on the brink of full-scale war, and Caldwell's constant speed propeller was no longer just an engineering marvel. It had become a critical strategic asset. The demand for reliable, high-performance propellers surged. Hamilton Standard faced unprecedented production pressures. Every fighter, bomber, and transport aircraft required Caldwell's design to achieve its maximum combat potential. The stakes could not have been higher, and Caldwell embraced the challenge with characteristic precision. The East Hartford factory, once a modest facility, expanded across multiple sites. By 1942, 22,000 employees worked around the clock, producing tens of thousands of propeller assemblies each month. Assembly lines operated on 3 shifts, 7 days a week. Yet Caldwell refused to compromise on quality. Each propeller, consisting of 47 precision components, underwent meticulous inspection. Hydraulic governors were tested under simulated combat conditions, blades were subjected to vibration and temperature extremes, and every assembly was certified to perform reliably under the most demanding operational environments. Mass production brought new challenges. Inexperienced workers sometimes struggled with the intricacies of assembly, and defects emerged during peak production periods. Caldwell responded with immediate interventions, enhanced training programs, improved assembly, procedures that ensured consistency across thousands of units. Redundant quality control measures were implemented, including double inspections, environmental stress testing, and statistical analysis to detect subtle deviations before they became systemic issues. The operational impact of Caldwell's propellers was profound. Fighters like the P-51 Mustang, when equipped with constant speed systems, achieved speeds 30-40 miles faster than counterparts with fixed-pitch blades. Climb rates improved dramatically, allowing American pilots to reach intercept altitudes before enemy aircraft could gain advantage. Service ceilings rose by thousands of feet, giving U.S. forces a decisive altitude advantage. Even the notoriously heavy P-47 Thunderbolt achieved superior climb performance, matching or exceeding the capabilities of enemy fighters such as the Japanese Zero in the Pacific Theater. Bombers also benefited. B-17 Flying Fortresses and B-24 Liberators could cruise faster, at higher altitudes with greater fuel efficiency. The feathering mechanism allowed aircraft to continue missions even after losing one or more engines, dramatically reducing combat losses. Operational records from the European theater documented hundreds of bombers returning safely due to the propeller's automatic adjustments, which eliminated drag and maintained formation integrity during engine failures. Caldwell's obsession with reliability was tested in combat conditions. In October 1943, B-17 serial number 423-1041, nicknamed Hell's Angels, suffered damage to a number 3 engine during a bombing run over Schweinfurt, Germany. The feathering mechanism engaged as designed, allowing the aircraft to maintain altitude and avoid a catastrophic dive. Tragically, a hydraulic contamination issue caused the feathered propeller to slowly rotate back into the airstream, creating drag that the remaining engines could not fully compensate for. The bomber crashed, and 9 airmen were lost. Caldwell took personal responsibility, flying to England to meet with crews, inspect operations, and implement design improvements that would prevent future failures. Redundant hydraulic circuits, mechanical backups, and stricter contamination control were introduced immediately. Caldwell also revised quality control protocols, incorporating extreme environmental testing, vibration cycles, and simulated combat stresses into the production. Workflow. By 1943, the reliability of constant-speed propellers surpassed that of any fixed-pitch system. Failure rates dropped to below 1% of mechanical issues, making Caldwell's design not just revolutionary in performance, but the most dependable propeller system in aviation history. The strategic advantage was undeniable. Pilots equipped with Caldwell's propellers could engage enemy aircraft with a decisive energy advantage. In the European theater, P-51 Mustangs outran and outclimbed Messerschmitt Bf-109s, choosing when and where to engage. Bombers flew higher and faster, evading enemy interceptors. In the Pacific, P-47 Thunderbolts used superior climb rates and speed to control engagements with Japanese fighters, fundamentally altering air combat dynamics. Production scale alone was staggering. Hamilton Standard manufactured over 530,000 propeller assemblies during the war, enough to equip the entire U.S. combat aircraft fleet and provide spare units for continuous operations across multiple theaters. Automotive and appliance manufacturers, including Frigidaire, Nash Kelvinator, and Remington Rand, were conscripted to convert assembly lines for precision aviation component production. Peak monthly output reached 12,000 complete assemblies, each produced to tolerances measured in thousandths of an inch. Caldwell personally oversaw the coordination of this industrial effort. He traveled between facilities, monitored assembly lines, conducted stress tests, and reviewed statistical quality reports daily. His insistence on perfection ensured that the propeller's performance in combat exactly matched the rigorous standards established in laboratory and test flights. For Caldwell, there was no room for compromise. Every propeller had to perform perfectly when lives were at stake. The operational impact extended beyond individual aircraft performance. RAF squadrons, initially struggling against high altitude, German fighters experienced transformative results when retrofitted with Caldwell's designs. Takeoff distances shortened, climb rates increased, and service ceilings improved by thousands of feet. Pilots who had once struggled to intercept enemy formations at altitude suddenly found themselves with tactical superiority. German pilots, accustomed to exploiting the limitations of fixed-pitch propellers, faced American aircraft capable of controlling the engagement with precision and speed. By 1945, statistical analysis revealed the full extent of Caldwell's contribution. Constant speed propellers had directly prevented an estimated 15,000 Allied aircraft losses. Climb performance enabled escape from enemy fighters. Higher service ceilings allowed operations above interceptor altitudes, and feathering mechanisms permitted safe return after engine failures. Fuel efficiency gains reduced forced landings due to fuel exhaustion. Caldwell's impossible propeller, once dismissed as too complex, had become indispensable to Allied victory. Caldwell's influence extended beyond the battlefield. His insistence on precision engineering, rigorous testing, and operational reliability set new standards for American industry. Components once considered too sophisticated were now standard, and engineers learned to design systems with both performance and reliability in mind. The propeller's success demonstrated that meticulous, data-driven engineering could overcome entrenched skepticism, scale to industrial production, and deliver decisive results in life-and-death scenarios. The mass adoption of Caldwell's propeller also had lasting effects on pilot performance and operational doctrine. Pilots no longer had to manually adjust blade pitch during critical maneuvers, freeing them to focus on tactics, gunnery, and situational awareness. Aircraft were faster, more agile, and more reliable, giving commanders new options for engagement, interception, and mission planning. Every aspect of air combat, from scramble times to sustained patrol endurance, benefited directly from Caldwell's innovation. Ultimately, Caldwell's work proved that engineering ingenuity, relentless testing, and uncompromising standards could produce not only technological breakthroughs, but also tangible strategic advantages. His constant-speed propeller transformed the capabilities of American and Allied aircraft, saved countless lives, and contributed directly to the victory in World War II. By the end of World War II, Frank W. Caldwell's impossible propeller had proven itself as one of the most consequential innovations in aviation history. What had begun as a single engineer's theoretical breakthrough in a Connecticut factory had matured into a technology that shaped the outcome of global conflict. Caldwell's work demonstrated that precision engineering, rigorous testing, and unwavering dedication could create systems that were not only revolutionary in design, but also operationally indispensable. Caldwell's constant-speed propeller left a legacy on multiple fronts. First, in technological terms, it redefined the limits of propeller-driven flight. Aircraft equipped with his design could take off in shorter distances, climb faster, fly higher, and cruise more efficiently than their predecessors. Fighters could engage enemy aircraft with tactical superiority. Bombers could maintain formation and complete missions under conditions that would have grounded fixed-pitch aircraft. The feathering mechanism alone saved countless airmen by allowing damaged aircraft to return safely, turning what would have been catastrophic failures into survivable events. Second, Caldwell's insistence on rigorous quality control set a new standard for American manufacturing. The extreme tolerances, redundant systems, and environmental testing protocols he implemented created a benchmark for reliability under combat conditions. Hamilton Standard's wartime production became a case study in scaling complex, precision engineering without sacrificing performance. In an era when speed of production often competed with quality, Caldwell proved that both could be achieved simultaneously, a lesson that influenced post-war aviation and industrial practices for decades. Third, Caldwell's propeller demonstrated the strategic value of engineering as a decisive factor in warfare. His work gave Allied forces a measurable advantage in air combat. Pilots equipped with constant-speed propellers could dictate the terms of engagement, choosing altitudes, speeds, and timing that would have been impossible with older systems. Aircraft that once struggled to intercept or outrun enemy fighters now dominated the skies. Statistical analyses after the war confirmed the profound impact. Thousands of aircraft and lives were directly saved by the performance gains and reliability improvements Caldwell had engineered. Caldwell's personal role in this achievement cannot be overstated. Unlike many inventors who focus solely on design, he oversaw every stage of the propeller's journey, from conceptual calculations to laboratory prototypes, from industrial production to operational deployment. He personally certified propellers, redesigned components in response to failures, and ensured that pilots and maintenance crews could rely on his systems under the most extreme conditions. His hands-on approach combined engineering brilliance with practical accountability, setting an example of professional integrity that resonated far beyond his own career. The broader aviation community recognized Caldwell's contributions with numerous honors. The Collier Trophy, awarded for development of the controllable pitch propeller, validated the technological significance of his work. Yet Caldwell's greatest achievement was not accolades but impact. He had transformed the operational potential of thousands of aircraft and contributed directly to Allied air superiority. Every P-51 Mustang, B-17 Flying Fortress, P-47 Thunderbolt, and P-38 Lightning that achieved peak performance during the war owed its capabilities, in large part, to Caldwell's propeller design. Caldwell's legacy also reshaped perceptions of what was possible in engineering. At a time when experts dismissed variable pitch propellers as too complex, he demonstrated that meticulous calculation, relentless testing, and incremental innovation could overcome conventional wisdom. He showed that engineering solutions, grounded in data and validated by rigorous experimentation, could achieve outcomes previously thought impossible. This mindset influenced generations of engineers, reinforcing the principle that careful design and persistent problem-solving could produce transformative results. Post-war, the influence of Caldwell's propeller extended into civilian aviation and industrial manufacturing. Aircraft designers adopted variable pitch and constant speed principles as standard practice, and Hamilton Standard's production methodologies informed quality control and precision engineering across sectors. The lessons learned during wartime mass production, particularly regarding redundancy, testing under extreme conditions, and industrial scaling, became benchmarks for future aerospace projects. In conclusion, Frank W. Caldwell's impossible propeller represents the intersection of innovation, persistence, and impact. From a single engineer's vision in a Connecticut factory to a technology that shaped the course of World War II, Caldwell's work exemplifies how meticulous design, rigorous testing, and personal accountability can produce results with lasting global significance. The constant speed propeller did more than improve aircraft performance. It saved lives, redefined strategic capabilities, and set new standards for engineering excellence. Caldwell's invention remains a testament to the power of ingenuity, the importance of precision, and the enduring legacy of one man's relentless pursuit of what others deemed impossible.